having this recording, this will be easier for you to do your own personal task. And I will share the screen. So, can you see my screen now?
Yes. Yep.
A few words about the initial data for turbine. Once again, they are exactly the same like for the compressor. It's diameters, angles in several sections, and the length of the inlet, outlet areas, as well as for the blades. The number of blades, but we remember that the number of blades is not the strict value here. And we will need some additional information for the turbine too. It's more complex than for the compressor because we will use a different way for the profiling node by setting up the angles and the thickness. But I will tell you about this data a little bit later. And speaking about nozzle guide vane and rotor blade, for example, if you would like to use more section than just hub and shroud, for example, the middle one, I would say that for the rotor blade, it could be reasonable, but for the guide vane, as we can see, and I told you last time, that, for example, the angles of the guide vane and nozzle guide vane, I'm sorry, alpha 1, it doesn't change a lot along the head of the blades, so it's not necessary to use more than 2 sections for the nozzle guide vane. For rotor blades, 3 section could be okay, but for the nozzle guide vane, 2 is more than enough.
Okay.
And we will start with the nozzle guide vane. Again, the procedure is totally the same. I will not create the whole chain, just we'll use these blade gen parts. So please add these 2 parts for the place where it's convenient for you, and also give them the names like NGV and Rotor Blade. But for your individual task, obviously, you will need to add a turbo grid for each blade and to combine both turbo grid blocks in one CFX block. So we will start with the first blade, which is nozzle guide vane for turbine stator blade. Is our initial data. So the first step is exactly the same. We are selecting normal axle, and we will set up the location of the nozzle guide vane. And the coordinates of the nozzle guide vane will be the same as for the rotor blade for turbine. So we assume that here where is rest point, our 0, our beginning of coordinate system. So that is why we will have 0 and 0 here for that at the left. To the right, for that, of course, we will have 50. And as for the radius, hub radius at the left will be for us 421, and it will be the same for the second section at the right, 421. And for the shroud, again, the our coordinate will be constant, which is 457. So because it's not nothing is changing in the diameters. This was our assumption of our methods. And here, as for the mode of profiling, we need to select the second one, which is which will use the preacher approach to profile the turbine blades, and press OK. In this window, at this stage, we will not change any angles or diameters or any parameters. We need just to set up the number of blades. For NGV, it's 54 blades, and the number of layers in which we will perform the profiling. We will use 2, but again, for nozzle guide vane, it's more than enough. For rotor blade, you can have out 5 is okay, and we press OK. So you can see that the appearance of the windows for profiling using preacher approach is slightly different than for the turbine. We have the meridional view, B2B view, but the lower window is different. But first we will start again with setting up the parameters of the meridional section. Again, for the left boundary, the coordinates for horizontal will be -50. I've chosen not very good example for the turbine. I understood it now because the blade is not very high. It's quite, but okay. I will show you some approaches, and you will use these techniques for using future tasks. And for the right boundary, the horizontal coordinate will be 55. Again, it's in the middle of the axial gap, and this is the boundary by which two blades will be combined. Okay. So on the right here, we can see again 2 black points, which corresponds to the hub and shroud section, in which we can change our blade, and several gray points in which we can just see the appearance of our profile. We will start with the hub section. You can double click on this point or double click on wherever you like on this field, and you will have this window. So in this window, what parameters do we have and what parameters do we need to set up? So first of all, we'll need to set up the diameters of the leading edge and of the trailing edge. They will be standard for all variants. This is like more typical values for the diameters, and you can use the same. Maybe after you perform the profiling of your own blade and you will send it to Mr. Baturin, he will recommend you, for example, to decrease the diameters or other parameters. But for the first iteration, these numbers will be okay for all of you. Then we have the window to set up the value which is equal. Oh, I'm sorry. 90 minus beta 1 or alpha 0. These values you calculated during the previous stage, and now you need to set up here the value 90 minus these values. For the beta 1, for example, for beta 2, this window, omega 1 and omega 2, these are the angles of sharpening the shape of the blade, and this omega-1 and omega-2 also will be standard for all variants. And the last parameter that we have here is 90 minus gamma. Gamma is a stagger angle for your blade, and you have formulas how to calculate gamma. In the presentation by Mr. Baturin, this was, if I'm not mistaken, in chapter 7, Excel turbines, and you need to use this formula.
Yes.
So for the gamma for the rotor blade, you will use beta 1 and beta 2, and for the guide vane will be alpha 0 and alpha 1. And you will calculate this value, but in system again you need to set up the parameter 90 minus gamma you've calculated before.
Okay.
Actually, I recommend you to create this table, for example, in several sections like hub shroud, beta 1, beta 2, alpha 1, alpha 2, and just to calculate the values 90 minus the angle, and calculate gamma, and calculate the value 90 minus gamma, like to be prepared for just inserting these values into the system.
Okay. I just have a question, because I think that for guide vane, the gamma is the same value for each hub and shroud.
Almost the same, but yeah, because as you can see, yeah, just a second, alpha 0 is equal for both hub and shroud, and alpha 1 doesn't change a lot
Yes.
along the shape of the blade. That is why gamma will be approximately the same.
Okay.
Yeah, like you can see from my calculations. So let's start the first iteration for the hub section of the nozzle guide vane. So we will start with diameter of the leading cage, and on this slide actually you can see some other statistical data. How can you calculate the leading edge radius, trailing edge radius, sharpening angles, but we will start with this initial data. For the diameter of the leading edge, we will have the value of 6. This is for hub section for the nozzle guide vane. For the trailing edge diameter, 0.8 is okay for the first stage. This value, which is omega 1, we will have it like 35. Omega 2, which is equal to 2 into the default values, is okay for us. And now we need to set up to set up the other angles. You can see that here for a 90 minus alpha 0 you have minus, so you need to insert these values with minus. For alpha 0 actually we will have here 0, because alpha 0 is equal to 90 for us. For this window, for alpha 1, we will have 65.1. And for the gamma, it will be 51.6. Let's check for leading edge diameter 6 millimeters, for trailing edge diameter is 0.8, 35 for omega 1, 2 degrees for omega 2, 0 for 90 minus alpha 1, and 65.1 for 90 minus alpha 1. Gamma is equal to 51.6.
Yes.
And we press OK. We have forgotten to change the properties of our project, I mean to set up the millimeters as they work in units. So, and now we need to start to change the appearance of this blade because as you can see, the shape is not very nice now. What are the criteria here for the correctness of your profiling? First of all, the throat have to be at the trailing edge, like we have here, but it's not very nice now. So the channel between the blades, the passage, have to be converging. This part of the blade, this one, it should be without some, it should be smooth, it should be rather straight, without any like disturbances. And because we're, for example, here, because we're dealing with a hub section, the hub, no, it's for the rotor blade, sorry. And what instruments do we have here? As you can see, if you click on the suction side and pressure side, you can see some control points, like moving which you can change the shape of your blade. So using Bezier spline. And for example, when you, for example, when you're changing the shape of your blade using this control section, you can see that the, for example, throat, the position of the throat could be changed, and like this. And the another rule here is you can see that inside the blade there are some gray lines which are forming the shape of your blade. So, for example, this line and this line, they must not be must not be intersection between this line. For example, can you see this? This
Yes.
this problem. So this is not appropriate. So you couldn't have this shape of the blade. So I assume that all the criteria that you can use dealing with the shape of the turbine blades. So, and as Professor Baturin again say, that the appearance of the blade have to be beautiful. That's all.
Okay.
I cannot tell you in which way you need to move the points of this blade. I mean, concerning your case, but what can you also do to improve the appearance of your blade? You can. You can, for example, try to change the stagger angle for some amount. I don't know, let's try 55, for example. 90. I think it's better. You also can slightly change the omega 1 and omega 2 in order to get the better appearance of your blade, but all the time try to follow that this road is all the time near the trailing edge of your blades.
Okay.
Because every time it's very individual with each blade, with each parameters, which with your own angles. I don't know what can we improve here. And this part again should be rather straight. I would do this blade like having this straight line here in this area to avoid the flow separation during the CFD calculations.
Okay.
And with nozzle guide vane, as I told you, the parameters of the nozzle guide vane, they will not change a lot along the head of the blade. That is why you can, for example, you created the shape of the hub section, and you think that it's quite okay, quite normal. You can use exactly the same parameters for the shroud section. So you can copy them and use the same parameters for the shroud section as well. This is only valid for nozzle guide vane, not for the rotor blade. So, and we will do this procedure now. Except for the alpha one, of course. So we are going to the shroud section, and we will copy 6 for the leading edge diameter, 0.8 for the trailing edge diameter, 2 for omega 2, 35 for omega 1, 0 in this window, 49 was here for us, and alpha 1 will be 63 in shroud section. Actually, the first variant of the shroud section is not very bad. As you can see, we already have the stroke near the trailing edge of the blades. I would again slightly increase this part. As I told you, the example is not very for display. Again, when you will perform the first iteration with your blades, make the pictures and send them to me and to Mr. Baturin, okay?
Okay.
Okay.
Because it's, as you can see, it's not quite a logical process.
Mm-hmm.
Yeah, and something like this. I will do something like this. Maybe even more increase. Again, criteria: this road, the smooth line here, no intersection of the lines which are forming the profile of the blade. Yeah, converging channel. That's all for the first stage. And of course,
Prof, I have a question. But I've noticed that the position of the trough doesn't move. If we modify the shape of the blade, the position of that trough doesn't move in the leading edge, in the trailing edge.
For example, if you change the stagger angle, it will slightly move here, maybe even, or like this.
Okay. Okay.
Maybe
Perfect.
because you didn't change a lot the, or like this, not very beautiful blade, or like this, and also maybe not this.
Because if you modify manually the position,
So
okay, it changed.
if you
Perfect.
increase this part more, so the throat will move, because here now you have greater greater area in near the leading edge. So just try to modify some point more.
Okay. Perfect. Thank you.
And the last criteria here is the pitch chord ratio used for the compressor too. So for the turbine, again, the value from 0.8 to approximately 1. And we will create pitch chord ratio now for, sorry. So for hub section, the pitch chord ratio is 0.64 approximately. For shroud, it's almost the same. But yes, we can see that the blades are located quite closer to each other. So maybe we can decrease the number of blades. Again, here try to use simple numbers, like maybe 49. 47 maybe. 45. So at the shroud section now we have 0.8. At hub section we have 0.7. Let's relate. I would say that at the hub section the distance is okay now, and I don't think that it's reasonable to decrease the number of blades more. And this is our nozzle guide vane. So speaking about the twisting of the blades, now you can see that this blade is rather straight along the head. And do not forget to perform this part 2 stack blade on centroid. And I think for the nozzle guide vane, that's all. More interesting parameters and more instruments we will use for the rotor blade. So if you do not have questions here, let's move to the rotor blade. Yes.
Yes.
In the end, there are 45 blades, right?
45 blades. Yeah.
And just about pitch ratio, can you tell normally the numbers that we need to have?
From 0.8 till 1.
Okay. Okay, 0.8 for hub and approximately 1 for shroud, approximately. No?
Both of this section could be in this range.
Okay. Okay. Okay.
Just a second, I will follow my notes. Yeah. We've done everything for the nozzle guide vane, and we can switch to the rotor blade. Let's start with geometry. So the location of the rotor blade will be the same. Like here we have 50, 55, so 60 for that. And plus 40 for on the right we will have 100, exactly as for compressor. And for the radius, yeah. In the first section, oh, just a second. Yeah, in the first section, the same like we introduced for the nozzle guide vane. In the second section for the hub, we will have 480. And for the shroud section, 460. We need to be sure that the appropriate mod is selected. Everything is okay. We press OK. Here, once again, we are setting up the number of blades, which is 106 in my case, and the number of layers is 2. And press OK. We are going to model properties and setting up millimeters. Then we need again to deal with meridional section. So for the left boundary, 55 for horizontal coordinate, and for the right boundary it will be 140. And the message here is exactly as for the nozzle guide vane, but with some specific features concerning diameters of the inlet of the leading cage and the trailing cage, the hub and shroud section. So the values will be different. So we're starting with the hub section. For the sharpening angles, omega-1 and omega-2, they are the same, 35 and 2 degrees. As for diameters, for the hub section, the diameter of leading gauge is 4 millimeters. For the trailing edge, 0.8 for hub section is okay. Just a second. I will move my table. And now we need to set up the angles. So here in this window, the value will be minus 38.2. For beta 2 in hub section, here we will have 57.7. And gamma in hub section will be 25.75. So we press OK. So here with the rotor blade, the first rules are the same of the stroke, of the smooth channel, of the straight shape of your profile here in this area. But Also, for the rotor blade, you need to consider the ratio of the areas at the hub section and at the shroud section. So hub section have to be thicker. And when you move the points of the control points of the Bezier curve for the hub section, try not to do the hub section very thin. Of course, we will move the points for the shroud section as we've done for the compressor, but from the very beginning, try not to do the hub section very small. So again, I would do this one higher. Like this. But I've forgotten about this throat, so maybe we can correct this throat changing the stagger angle, maybe 30. Not very good. 37. Okay, let's have 35. And now we need to correct the position. I don't know, maybe you have different picture because you've changed the position of different points, but in my case I need to change the position of this road closer to the trailing edge.
Because for rotor blade, what's the best position for the throat?
Exactly the same as for the normal vein, near the trailing edge of the blades. Something like this. Yeah, you can see that this turbine blade is not very big. The size is quite small. That is why I cannot do very huge hub section, like very thick hub section. But maybe in your case, your blade will be taller, and you will be able to create a hub section bigger than in my case. Actually, we can measure the ratio of the areas right now. So the rule here for the areas for the rotor blade of turbine is that the hub section area have to be 3 times bigger than the shroud one. Now we do not have this situation. That is why the first step for us is to move by hands these points. So we select leading edge, and we're moving the first point. We select in the trailing edge, and we move this point. Maybe even more. If you cannot get the difference of 2 times between these areas, so the second solution is to try to increase the area, changing the control points. But I think for my case, because the blade is quite small, I will leave it like this. So 340 till 200, something.
We should have 3 times more. Okay, 3 times more.
But I think in my case it's not quite possible. If you have the same situation like me, 2 times and 2 times a half could be okay. So for small blades could be okay if you cannot increase this area, but preferably 3 times bigger the hub section. Just I will try to no. Because as you can see, if I'm trying to increase the area of the hub section, the position of the throat changing is going to, towards the trailing edge, or I'm sorry, releasing edge. Maybe in this case we need to think about the compromise between the area and the position of the throat. So, but the position of the throat, of course, is the criteria which is number one.
Okay.
Going to the shroud section of the rotor blade, we will use the following parameters. For omega 1, 20. For omega 2, 2 is okay. For diameter of leading edge is 1.5. The diameter of trailing edge will be 0.798. So, for example, if you would like to do more than 2 sections, I mean, if you would like to include the middle section in your calculation too, speaking about diameters, of course, you can select some middle value between the diameter at the leading edge at the shroud section and the leading diameter for the hub section. The same for the other parameters. Let's do the angles. For beta 1, we will have the value of minus 26.7. For beta 2, we will have 59.6. And for gamma, we will have, okay, let's do 37. Not very nice.
That's so beautiful.
Not very nice blade. And now, moving these points, we need to create more beautiful blade. So I would say that for the shroud section, it's easier to create the good blade because the profile here is quite thin, and you do not need to think a lot about the area, so you can correct this area at the stage of creating hub section. And yes, but let's check this area now. So what I would do in this case, this part is quite okay. Maybe I would try to change the stagger angle to 30. No, not 30. Okay. No. I think this appearance is better now. And the location of this road is okay. The only thing I don't like about this blade is this part. Maybe it's too curved. Not very good blade from the very beginning. maybe something like this. I would do something like this, but also we need to check the area. Quite okay.
Okay. Yeah, more or less 3 times more. Yeah.
So 350 here and 150 here. So cold, but it's better than before. The location of this road is okay. The lines are not intersecting. Yeah. And the last parameter here for us is obviously pitch chord ratio. Again, the rule is the same, but already you can see that the distance between blades at the shroud section is quite big, but at hub section is quite small. So in this case, of course, we will not find the ideal solution for both sections. So we will need to think about some compromise. But I would start with hub section. And for hub section, we have 0.5. For shroud, it's 0.8. So let's try to decrease the number of blades. Maybe 99. Not up. Okay, 93. As we can see, the distance between the blades is already too far at the shroud section, and the further decreasing of the number of blades, it's not very good. Actually, I will do 95, maybe, or even leave for 97. Yeah, in this case, we will not get good ratio for the hub section, unfortunately. But this could be such situation.
Okay.
We need to stack the blade on centroid. And we can see the appearance of our blade. I've lost my blade. Something like this. So as you can see, it's not, the profiling is not so logical as for Turbine, and I understand that it's complicated for you because you do not have the experience in this area, and you do not know whether it's good blade or bad blade. So again, the idea for this stage is to perform the first iteration with your blades, send your results, get some recommendations, and to correct the shape of your blade. The results, interesting results, will be of course the B2B section with the location of this road, the area for the cup and shroud section, and pitch chord ratio, and the number of blades. And meridianal section as well will be useful to see what here can be done to improve. Something like this with Turbine.
Okay.
Okay.
Maybe some questions with which I can help you at this period, at this stage.
Oh, I think we will proceed this and then we will see.
Yeah, I think it's better to try to do this process with your own parameters. Uh, prepare this table. Do not forget that it's 90 minus the angle. All the necessary data you have. And I think it's better to try to do it by yourself. And then we will deal with the results.
Yes, okay. And for the geometry, we don't need to make approximation of equal radius or something like this as you have, no? Because you, in your document, you have, for instance, the same diameter at inlet and outlet. For us, it's not the same.
Okay. Maybe you have different results.
Yes.
Could be like this. No, you do not need to do these approximations.
Okay, okay.
So
Okay, we take our values.
Yeah, just use your own results. The only thing that you will have the same is the location of the blades. Like here is 0, and the length of the inlet and outlet area, and the size of the axle gap. That's all. The other parameters are yours.
And I have a question about the pitch chord ratio. And we have seen that this value depends on the number of blades. And in the first approximation, if is like in our case is 0.6, 0.65 for the hub section. What are the parameters that have the most influence in this?
Except for the number of blades, you mean?
Yes. For example, the area, or I don't know, the angle of attack, something similar.
This problem probably, I mean, of the low pitch chord ratio you will have for the hub section more likely. Of course, the like not big, but some influence will be of the area of the blade itself, but you cannot decrease it very much because this is the hub section. So for the hub section, more likely you will have the low number of the pitch chord ratio. Also, you can try to change the stagger angle for this section. And also you can try to change the sharpening angle omega 1.
Okay, perfect.
This is very individually, so we need just to see the first iteration of your blades.
Okay.
To give some recommendations.
Okay, thank you.
Any other questions?
No. For me, it's okay.
No, for me too.
No, for me too.
Sorry, once again?
It's okay.
It's okay.
Yeah,
Okay.
it's okay.
So try to do this this process using your data, and we will wait for your results. For the compressor guys, it's the same, but I think with you it will be easy and more logical for the compressors. So
Okay.
me and Mr. Baturin, we are waiting for your results.
Okay, perfect.
Thank you very much.
Okay, then have a nice day, and
Thank you.
let's stay in contact.
Okay,
Yeah,
let's
sure.
keep in touch. Thank you.
Thank
Daria.
you. Have a
Thank
nice
you.
day too.
Have a nice day.
See you.
Bye.
Bye.
Bye bye.
Bye.